Hi everyone, greetings of the day. I am Dr. B. Ravi Chandra. Today, let me discuss about the problem which is related to the design of FIR filter, linear phase FIR filter using some different types of windowing techniques. In the last lecture, we have discussed about the topics which is related to the designing of linear phase FIR filter by using the windowing techniques. In that session, we discussed what is meant by windowing and what is meant by different types of windowing techniques and what are the steps that involves in designing the design of a linear phase FIR filter. So based on that particular last session, let me have some different problems on different types of windowing techniques like Hamming window, rectangular window and panning window. So I have taken one example for each technique, and let me see what the process, how the process is going to take place for designing this linear phase FIR filter. So just contents what in today's lecture I am going to discuss the problems on first technique, which is Hamming window, second technique rectangular, and third technique Hamming window. Right. So first problem, what he is asking, design a high pass filter with the following frequency response. We know that we will be given with a following frequency response, and he has to design the high pass filter. He has to design the high pass filter by giving one desired frequency response, which is HD of e power j omega is equal to 1 within the conditions, that is pi by 4 less than or equal to omega less than or equal to pi, and it will be 0 in the remaining ranges. So according to this condition, what is the range? From the range between minus pi to minus pi by 4 or else pi by 4 to plus pi, the value will be equal to 1. In the rest of the thing, the value will be equal to 0. So this is the condition given in the question, and he has to design the high pass filter by using the Hamming window. So what is the length he is given? He had given the length n is equal to 11. So by all this specification, let me see step by step how we are going to design this linear filter, high pass filter. In the first step, we are going to find out the value of desired impulse response, that is HD of n. We know the equation, HD of n is equal to 1 by 2 pi integral minus pi to plus pi HD of e power j omega into e power j omega and d omega. So this is the actual equation for the desired impulse response. And what is the condition they have given in the question? HD of e power j omega is equal to 1. So within the range pi by 4 to pi. So instead of this HD of e power j omega, we got two conditions, that is it will be equal to 1 between the range minus pi to minus pi by 4, and it will be equal to 1 from pi by 4 to pi. So I have taken two conditions according to the diagram. Let's see here, minus pi to minus pi by 4 one condition, pi by 4 to pi it will be equal to 1. So in the rest of the reason the value will be equal to 0. So that's why I have taken two integrals. So integral which is from minus pi to minus pi by 4, the value will be equal to 1, and similarly the integral pi by 4 to pi, the value will be equal to 1. So two integrals I got, and the rest of the thing we know that doing the mathematical expressions, so integral e power j omega, we can write it as e power j omega n by j n. So within the limits minus pi to minus pi by 4. Similarly, second integral, same, we are going to get e power j omega n by jn within the integrals limits pi to pi by 4. So applying the limits, upper limit that is pi by 4 to lower limit that is pi. Similarly for the second, upper limit it is 5 and lower limit is pi by 4. So rearranging this equation, I am rearranging this equation. Let's see here, e power j n pi minus e power minus j n pi. So one parameter I have taken. Similarly, the second parameter, second value, which is e power j n pi by 4 minus e power minus j n pi by 4. That means I have rearranged this equation in the form of e power j theta minus e power minus j theta divided by 2j. Okay, so I rearranged that particular equation in this form, so that what I am going to get, I can write this equation as sin n pi. Why? Because what is the value of n pi here? What is the value of theta? Theta is nothing but n pi. So sin theta. Similarly, for the second condition, it will be sin n pi by 4 by theta. So the value is theta. So overall, I formed this desired impulse response. What is HD of n? What I got here? Sin n pi minus sin n pi by 4 by pi n. So this is the desired impulse response which we derived in the first step. So next step, what we are going to do means just applying the values. We are going to find out the coefficient values of all HD of n. So what is the length they have given? Length is given as n is equal to 11. So how many we are going to find out? So here we need to find out the value. How many coefficient values we have to find? That is n minus 1 by 2, which is equal to, what is the value of n? 11 minus 1 by 2, that is equal to 10 divided by 2. Total how many values I need to find out? Total 5 values, that is HD of 0 to HD of 5. So total these many values we are going to find out to get the coefficients of desired impulse response HD of n. So first of all, by substituting the value of 0, n is equal to 0. Here if we substitute the value, it will becomes indeterminate. So overall the value will becomes indeterminate. For that, for this particular value n is equal to 0, I am going to apply the limits and then we are going to find out the value of HD of 0 for n is equal to 0. Only for the value n is equal to 0, this is the condition we need to do. Why? Because if we do the value n is equal to 0, the total expression will become indeterminate. So in that scenario, we cannot able to design the FIR filter. So only for that particular value n is equal to 0, we need to do this one. So that is applying the limits and finding the value. Later, from next onward, that is for n is equal to plus or minus 1, by applying the value of n is equal to 1 or else minus 1, we are going to find out the value. Similarly, for all n is equal to plus or minus 2, n is equal to plus or minus 3, because symmetrical values, plus or minus 3, plus or minus 4, plus or minus 5. So overall, we will get the values from n is equal to 0 to 5, which are nothing but coefficient values of HD of n. So overall, in the first step, we derived the equation HD of n. After deriving the equation HD of n, what we have done? We have substituted the values, that is n is equal to 0 to 5, and find out the values of all coefficients of desired impulse response. So first step we have completed. The second step, we are going to find out the value of windowing techniques. Now he asked to find out the value of, to design the high pass filter by using the Hamming window. So in the last lecture, we have studied about the Hamming window. The condition for the Hamming window is nothing but it will be equal to 0.54 plus 0.46 cos 2 pi n by n minus 1. When mod n less than or equal to n minus 1 by 2. Otherwise, the value will be equal to 0. So this is the condition which is related to the Hamming window. So by using this Hamming window sequence, we are going to design the high pass filter. Fine. Now we are considering for n is equal to 0 Hamming window, and the value lies between minus 5 less than or equal to n less than or equal to 5. Same. How many values we are going to find out here? We are going to find out from minus 5 to plus 5. So see here, what I am going to substitute? I am going to substitute the values n is equal to minus 5 to plus 5. That is all positive and negative values symmetrically. If I substitute the total values in n is equal to 0. So what is the value? Substituting n is equal to 0 in this thing, I am going to get the value 1. Similarly, substituting n is equal to 1, 2, 3, 4, 5. Overall, I got all the coefficients of the Hamming window sequences. So what the sequences I got here? I got all the 5 sequences of the Hamming window. So 2 steps I got. We have found here. First one is HD of n. Second one is Hamming window sequences. In the next step, we are going to find out the transfer function, that is final FIR filter coefficients, and we came to know across that how to find out the value of the FIR filter coefficients. So this is the equation which is nothing but to find out the value of H of n. It will be obtained by multiplying the desired impulse response HD of n with the windowing sequence W of n. So we found these in first step. Step 1, we found all the coefficients in step 1, and we found all the coefficients of Hamming window in step 2. So we got total 5 values here and 5 values here. Now what we are doing here, we are multiplying the 2 coefficients, desired impulse response coefficient HD of n and Hamming window coefficient response W of n. So after multiplying this, overall how many we are going to get? We are going to get all the FIR filter coefficient from H of 0 to H of 5. So these are all the values we find in the third step. So we got total 3 we got. One is hd of n in the first step, w of n in the second step, and the third step, by multiplying first and second step values, we are going to find out the value of h of n, which is nothing but the FIR filter coefficients. And the fourth step, this is the equation. Now this is the equation. What the scenario, what is the agenda we have to do here? We want to find out the transfer function of the FIR filter. That's why we know the value h of z is equal to h of 0 plus summation n is equal to 1 to n minus 1 by 2 h of n z power minus n plus z power n. This is the actual equation to find out the transfer function of the FIR filter. Now here we know how many values here. N is equal to 11. Na? So n is equal to 11 means from n is equal to 1 to 5. So n is equal to 1 to 5 h of n z power minus n plus z power n. By expanding that summation, what we are going to find out, what is the value of h of 0? We know that the h of 0 is nothing but 0.75 plus h of 1 into z power minus 1 plus z power 1. That is, this all the values when I substitute n is equal to 1. This is all the values when I substitute n is equal to 2. And this is the values when I substitute n is equal to 3 and n is equal to 4 and finally n is equal to 5. So by expanding the summation, the equation what I got is that nothing but transfer function of the FIR filter. So after expanding, just substituting the value of h of 1, h of 2, h of 3, h of 4 and h of 5. Here we cannot able to see the value of h of 4. Why? Because the value of h of 4 is equal to 0. That's why that particular term has been omitted. So we have removed that particular term. And what is the final equation I got here? H of z is equal to this one. Now if you observe this equation, you can see the powers of positive. So all the powers in each and every term, you can see the power, positive powers. So here we can say that we already studied in the steps where the equation which is formed h of z, which is nothing but the transfer function of FIR filter, which contains all the positive powers, it is nothing but anti-causal filter. So this anti-causal filter is very difficult to realize. Why? Because all the positive factors are positive powers are obtained in that particular equation. So this is very difficult to realize that FIR filter. So in that problem, to overcome that problem, in the last step, what we are going to find out, just we are finding the new transfer function h inverse of z by multiplying the h of z with z power minus n minus 1 by 2. So here if we calculate this z power n minus 1 by 2, that is 11 minus 1 by 2, 10 by 2, that is z power minus 5. So in the last step, to convert the anti-causal filter into causal filter, what we are doing, we are multiplying the formed transfer function with z power minus of n minus 1 by 2. Here what is the value? Here n is equal to 11. That's why we are multiplying that particular transfer function with z power minus 5. So see here. So we are multiplying z power minus 5. After multiplying all the z power minus 5, you can see z power minus 5 into 0.75, z power minus 5 into z power minus 1 into z power minus 1, z power 1. So if I get all the powers which is in a positive will be converted into negative. So you can see by multiplying all the term with z power minus 5, you can see all the powers which is in positive has been converted into negative, so that by rearranging the equation, h inverse of z is equal to, you can see z power minus 10, z power minus 8, minus 7, minus 6, minus 5, minus 4, minus 3, minus 2 and finally 0.0036. That is, we just converted the anti-causal filter into causal filter. So with the help of this particular equation formed by multiplying with z power minus 5, we can able to draw this, or we can realize this particular term in the form of high pass filter. So these are the finalized coefficients what we formed. If you see here, the common values is h of 0 and h of 10. The common value or the term 0.036 is common to h of 0. What is the value here? You can see h of 0 and h of 10. So 0.0036 if I take common, it will be 1 plus z power minus 10. Similarly, h of 1 is common to h of 9. So that is, if I take the common value 0.03, the value will be 0.03 into z power minus 8 plus z power minus 2. Similarly, h of 2 is equal to h of 7, h of 3 is equal to h of 6 and finally h of 5 is the single term. Same, by taking the common terms, what are the coefficients we formed here? The coefficients are h of 0 is equal to h of 10 is equal to 0.0036, and similarly with the help of all this transfer function and with the help of all this coefficient function, we can draw the finalized high pass filter by using any type of diagrams like direct form 1, direct form 2 or parallel, whatever it may be, which we have discussed in the previous sessions. So like this, how we are going to design the high pass filter by using the Hamming window by following all the steps, like step 1, first finding the value of HD of n, the step 1, in the step 2 we have for finding the value of Hamming window, that is W of n, and the step 3 finding the value of h of n, which is nothing but HD of n into W of n. In step 4 finding all the values, finding the transfer function of FIR filter, which is h of z. So here in the step 4 what we got anti-causal filter, which is unable to draw the, or which is not realizable to draw the FIR filter. For that, what we have done in the 5th step, just we have multiplied the transfer function h of z with z power minus of n minus 1 by 2, so that anti-causal filter is converted into a causal filter where we can realize that particular transfer function, so that the FIR filter of high pass filter can be realizable. So like this we can follow these 5 steps to find out or to design the FIR filter with Hamming window. Similarly, I have taken another windowing technique, which is nothing but rectangular window. Same, you can see the specifications. The specifications are somewhat different when we compare with the another before problem. Say, so it is some different kind of model. So he had given the passband gain of unity, cutoff frequency 1000 Hz, sampling frequency 5000 Hz, and similarly length also you have given m is equal to 7. So with this, if we draw the desired frequency response of that low pass filter, see here what he told, HD of e power j omega is equal to 1 when within the range minus 2 pi by 5 less than or equal to omega less than or equal to 2 pi by 5. So with this, within this region, the value will be equal to 1. So remaining value will be equal to 0. So this region we can call it as a passband region, and the remaining values which all contains 0 is said to be a stop band region. So this is the condition he has, and he has to find out to design the low pass filter by using the rectangular window. Fine. Let me see. The steps will be same, but the only difference is that we are using which windowing technique now? We are using the rectangular windowing technique. That is the only difference. The rest of the thing will be same. So in the first step, we are just finding the value of HD of n with the same equation, and here the limits ranges between minus 2 pi by 5 to plus 2 pi by 5. And what is the value of HD of e power j omega? HD of e power j omega is equal to 1. Just I am substituting the value 1 into e power j omega n, and considering the integral, doing the integral, and we got e power j omega n by jn. Then applying the limits, rearranging the equation. See, it is in the form of e power j theta minus e power minus j theta divided by theta. So it is in the form of this condition, and this is nothing but the sine theta. Sine theta is nothing but 2 pi n by 5, which resembles the value theta is equal to 2 pi n by 5. So what is the final equation I got here? HD of n is equal to 1 by pi n into sine 2 pi n by 5. So in the first step we found the value of HD of n. So now how many values we are going to find out here? We want to find out the values. The length what he had given, n is equal to 7, that is 7 minus 1 by 2, that is equal to 6 by 2, total 3, up to 3, that is from 0 to 3 we are going to find out. So 0 to plus or minus 3 values. So same, if we substitute the value of n is equal to 0 directly into the HD of n, it will be indeterminate, so that the first value will be done by applying the limits. So after applying the limits, HD of 0 is equal to limit n tends to 0 sine 2 pi n by 5 by pi n, the value will becomes 0.3027, and the rest from next value, that is from n is equal to 1 onwards, just we will substitute the value in the equation, and finally we are going to get the values of coefficients which is related to the desired impulse response HD of n. So in the first step we found all the coefficient values of desired functions from n is equal to 0 to n is equal to 3. Fine. In the next step, he has to find out to design the low pass filter by using the rectangular window. Just if he has to find out that by using the rectangular window, just you need to recall the condition. What is the rectangular window condition? He says that WR of n is equal to 1. That is mod n less than or equal to n minus 1 by 2. That is from 3 minus 3 less than or equal to n less than or equal to 3. In that condition, the value will be equal to 1. So there is nothing to do the values. Why? Because directly he had given the value will be equal to 1. So whatever the values from n is equal to minus 3 to plus 3, all the values will be equal to, that is WR of 0 to WR of 3. Whatever you do, the values will be equal to 1. Just so 1. Everything will be equal to 1. So what here? We can see that the rectangular window coefficients will be equal to 1 for all the values which resembles from minus 3 to plus 3. So from the condition, from the ranges from minus 3 to plus 3, the value of all the coefficients of rectangular window sequence is equal to 1. Now in the third step, now we have find out the filter coefficients of FIR filter, which is nothing but h of n, and we know that by multiplying the desired impulse response with windowing sequence, we can find out the value of all these h of n. See here, h of 0 is equal to, when I substitute n is equal to 0, hd of n value, it is 0.4, and if you see here, all the rectangular window sequences are equal to 1 only. See here, 1, 1, 1, 1. Why? Because directly the condition has given within any range, that is according to our length n is equal to 7, the values from minus 3 to plus 3, the value will be equal to 1. So that's why all the windowing sequence, rectangular windowing sequence is equal to 1. Just we are multiplying all the ones with hd of n values, we get the values of filter coefficient, that is h of n. And finally, just transfer function, we know that h of z is equal to h of 0 plus summation n is equal to 1 to 3 h of n z power minus n plus z power n. Substituting the values, we get the h of z, and which is an anti-causal filter. Why? Because all the factors, all the terms are containing with positive factors, that is z power, positive powers, that is z power 1, z power 2, z power 3, which is, it resembles that it is nothing but a anti-causal filter where it is very difficult to realize. So it is very difficult to realize what we are doing. We are converting this anti-causal to causal, that is h inverse of z. How we are going to convert? Just we are multiplying this h of z with z power minus of n minus 1 by 2. So according to this, the value will be equal to z power minus 3. So the formed equation h of z is multiplied with z power minus 3, where all the positive powers are converted into negative powers. You can see here, z power 1 means z power minus 3, z power minus 2, z power minus 1 and z power 0. So you cannot see any positive power factors, so that we can directly say that the formed equation is nothing but the causal filter, where with the help of this causal filter we can realize that particular FIR filter. So you can see, after rearranging the things, the common factor, if I take the common factor 0.0623, it will be z power minus 6 plus 1. So see here, what are the common factor? The h of 0 and h of 6 values will be equal to same, and h of n and h of 5 factors will be same, h of 2 and h of 4 will be same, and finally the unique term h of 3 is equal to 0.4. So with the help of these particular coefficients, we can draw or we can realize that low pass filter with any type of structures like direct form 1, direct form 2, lattice structure or parallel cascade form, we can realize that particular things. So with the help of these coefficients, we can draw the low pass filter, LPF. Okay, so this is another technique how we can design the low pass filter by using the rectangular windowing technique, which we followed all the 5 steps, and how we can realize that particular equation formed here, h inverse of z. And finally we will end up this lecture with another technique, which is nothing but the Hanning window. Same, I can say that I can repeat the same thing, where it follows all the same steps. Only the thing is, in the third step, instead of Hamming window, here instead of another window, he has to find out Hanning window. So here only we can see the differences. Rest of the things will be same. So what he asked, hd of e power j omega is equal to 1. When it will be 1, it will be 1. Between the range minus pi to minus pi by 4, it will be equal to 1, and pi by 4 to pi, it will be equal to 1. Rest of the things, the values will be equal to 0. So according to this condition, he has to design the high pass filter by using the frequency response, by using which windowing technique? Hanning windowing technique. And the length what he had given here, n is equal to 11. So by using all the specifications, let me quickly see the steps what we have already studied in the previous two problems. Let me see the steps how we are going to design this ideal high pass filter. Same, first step. First we need to find out the impulse response HD of n. Same, what is the value of HD of e power j omega? The value will be equal to 1, and within the conditions, within the range minus pi to minus pi by 4, it is first term, and similarly pi by 5 to pi by 4 to pi, it is the second term. After applying the limits, after doing the integral part and applying the limits, the finalized equation what we are going to get? We are going to get HD of n is equal to 1 by pi n sin theta, that is e power j theta. Here we have rearranged all the terms in the form of this condition, e power j theta minus e power minus j theta by 2j, that is equal to sin theta. So according to this condition, the finalized equation, desired impulse response HD of n is equal to 1 by pi n sin n pi minus sin n pi by 4. So here sin n pi, and the second term which is sin n pi by 4. So this is the finalized desired impulse response. So after forming this particular, we need to find out the coefficient values, that is from n is equal to 1 to n is equal to 0 to 5. Why? Because n is equal to 0 to 5, the value what he had given is n is equal to 11. So 11 minus 1 by 2, which is equal to 5. So total 5 terms. So from n is equal to 0 to 5, we will get all the coefficients value, which is nothing but this. So what is these values? These are nothing but the finalized impulse response sequences from HD of 0 to HD of plus or minus 5. So we got this. In the second step, we are going to find out all the Hanning window sequences. And what is the condition? We have to keep it in mind. If it is a Hanning condition, Hanning window technique, the condition is this one. That is WH of n is equal to 0.5 plus 0.5 cos n. So in this condition, we are going to finding all the sequences from n is equal to 0 to n is equal to 5. So same, we will get all the values, 1, this one, for 2 plus or minus 2, for plus or minus 3, for plus or minus 4, and plus or minus 5. We got all the 5 sequences, which is nothing but the Hanning window sequences. So after getting these sequences, in the third step, we are multiplying HD of n with windowing sequence. So whatever the values we got in HD of n, that is total 5 coefficient values, desired impulse response values, is multiplied with windowing sequence values. So by multiplying all the values, we will get the finalized values, which is nothing but impulse sequences, that is h of n from n is equal to 0 to 5. All the values from n is equal to 0 to 5, we get the values. So finally, after getting the value in the fourth step, we are going to find out the transfer function by using the equation. So substituting all the values which we found in the step 3, this is the equation we found here. See here, we got all the factors z power 1, z power 2 and z power 3, which is in the form of an anti-causal filter. So here it is very difficult to realize this anti-causal filter. So what we are going to do, we are going to multiply this h of z with a transfer function, h of z power minus of n minus 1 by 2. So that is equal to z power minus 5. So the formed equation h of z is multiplied with z power minus 5. So we are going to get the finalized value. We are going to get the finalized equation, h inverse of z is equal to z power minus 5, minus 4, minus 6, minus 3, minus 7, minus 2 and minus 8. After rearranging this equation, the finalized equation is h inverse of z is equal to, you can see here the common factors, 0.026, 0.026 if I take, the value will be z power minus 2 minus z power minus 8. Like this, if we see all the coefficients, 0, 0, minus 0.026, that is h of 0, 2, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, h of 10. So total 11 values. By considering all the value, here the arrow indicates the value starts with n is equal to 0. So the value starts here from n is equal to 0. If the arrow is indicated here, the value starts here. That is n is equal to 0 is the value. For n is equal to 0, the value will be here. So starting of the corresponding value where it starts means that will be indicated with the arrow mark. So if he had indicated here, that means the value of n is equal to starts from here, that is n is equal to 0 to n is equal to 10. So these are the total FIR causal filter coefficients. So with the help of all these causal filter coefficient, we can realize the high pass filter by using the Hanning window sequences. Like this, all the techniques what we discussed in the last lecture, by using windowing techniques, different types of windowing techniques and their conditions, we can design the FIR filter by using all the different types of windowing techniques.